Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. For billions of years, the universe has been recycling its core materials. Stars live, they die, and they scatter their elements back into the cosmic void, priming the next generation of planets and perhaps, life. Of all these recycled elements, carbon is arguably the most critical. It's the spine of every organic molecule on Earth, yet when we look out into the vast, dark spaces between stars, a fundamental accounting problem emerges. We can't find all the carbon. This is known as the Interstellar Smog Paradox. Based on the elemental composition of stars, the cosmic inventory, astronomers know exactly how much carbon should exist in the Milky Way's interstellar medium. However, when they survey the galaxy, identifying carbon locked up in traceable forms like carbon monoxide, CO, simple methane, CH4, or recognizable graphite grains, they consistently come up short. About 20% of the galactic carbon is simply missing from the ledger. So, where is this invisible 20%? It's not dark matter. This is regular, baryonic matter. The leading theory suggests this missing fraction exists as massive, complex, sheet-like polymer structures floating diffusely throughout space. Imagine enormous, ultra-thin films of organic material, far more complex than simple molecules, yet too disordered to be neat crystals. These sheets are thought to be built upon polycyclic aromatic hydrocarbons, or PAHs. PAHs are carbon molecules structured in hexagonal rings, similar to fragments of soot or burned toast, but they are abundant in space. We detect smaller PAHs easily because they fluoresce strongly when hit by ultraviolet radiation. But the larger they get, the trickier the detection becomes. When PAHs link together, they don't just form larger clumps of dust. They form vast, amorphous polymer networks, essentially, interstellar plastic. Because these structures are highly disordered and spread out like colossal, invisible sails, they don't absorb or emit light at the specific, sharp wavelengths that traditional spectroscopic methods rely on. They simply blend into the background, creating a kind of cosmic carbon smog that is spectrally silent. Think of it like trying to identify something based on its shadow. Small, precise molecules cast distinct shadows, sharp spectral lines. But a huge, diffuse sheet casts a blurry, featureless shadow that is almost indistinguishable from the background noise. This structural ambiguity is the key to the paradox. The polymers are so large they evade the simple signatures of gas, yet so dispersed they don't behave like solid dust grains. Recent scientific breakthroughs have attempted to address this. Researchers at facilities like the Spitzer Space Telescope and powerful radio arrays are looking not for the sharp lines of gas, but for the broad, faint hum associated with the bending and stretching of carbon-hydrogen bonds within these massive polymer sheets. Detecting this hum is an extraordinary challenge, requiring filtering out every other astronomical signal. The implications, however, are profound. If 20% of the Milky Way's carbon is locked up in these organic polymer sheets, it fundamentally changes our understanding of the cosmic carbon cycle. It means the interstellar medium is far richer in complex organic material than previously assumed. When new stars form, they condense out of these very clouds, meaning planets, moons, and asteroids are literally built from this invisible carbon smog. Every time a planet forms, it is likely seeded with these polymer sheets, which act as prebiotic reservoirs of complex chemistry. This isn't just about finding missing carbon. It's about locating the primary galactic reservoir of the complex chemistry necessary for life itself, floating unseen above us. Scientists are now running complex laboratory simulations, exposing PA molecules to radiation in extreme cold, mimicking interstellar conditions, to see if they spontaneously link into these massive polymer structures. The results are proving that this synthesis is not only possible but likely. The interstellar smog isn't empty space. It's a vast, dark factory quietly synthesizing the fundamental organic molecules that make our lives possible. The missing carbon isn't truly missing, it's just incredibly good at hiding in plain sight. For more incredible facts like this, don't forget to subscribe and turn on notifications.